My projects for this semester have used computer vision to develop a tennis ball detecting robot. For Project 1, I implemented the ball detecting mechanism. However, it was observed that the system had noise in the form of false positives. The first goal for Project 2 was to rectify this by reducing the influence of noise on the system. Other goals for this project included calculating the correction angle, which is the angle the robot needs to move through to directly face a tennis ball, as well as creating a ROS package that encapsulated all the required functionality. First, I worked to reduce the overall presence of noise in the system. This was done by tuning the parameters used in the ball detection algorithm. I adjusted values for color filtering, circle detection, the overall image contrast, and the number of times each image is blurred. This resulted in a very noticeable reduction of false positives. So next I wanted to reduce the influence of any remaining noise. In other words, I needed to distinguish the real detections or the expected detections from any extraneous noise or false positives. This was done through k-means clustering. If you recall from my Project 1 video, I require a consecutive number of detections to be reached before the program decides that something has been detected. So in order to determine the correct k values and initial means for the clustering operation, I use the image from the detection period with the greatest number of detections. So to illustrate what I mean by this, on the right we have the results of a clustering operation. The left image is the last frame of a detection period. I've included it to show the analog between the clustering operation and the real world. Also note that this was a trial done before the camera was tuned, so that's why it's so noisy. The important thing to note is that the image on the left has 5 detections on it, but the image on the right segments the data into 7 clusters. This is because through the detection period, there was an image that had 7 detections on it, which determined the K and the initial means. Hopefully it's readily seen that cluster 4, the cluster furthest right, belongs to the tennis ball, but I needed to get the computer to see it. To do so, I used the idea that tennis ball clusters are much more compact than noise clusters. We can see from the image that noise clusters have a lot more spread. To choose the correct cluster, I use a multi-stage filtering process, which I also call a voting process. First, in order to be considered a candidate, a cluster needs to reach a minimum number of data points. So if I require 100 points for the detection threshold, a cluster has to have at least 80 to be a candidate. Next, I compare the cluster densities for the remaining candidates. I define density as the number of points per cluster area. Cluster area is determined by the max centroidal distance. So the point in the cluster that's furthest away from the centroid, that distance serves as the radius of a circle. Finally, if no winner was chosen in the previous stage, I compare ground pixel distance between the 2 remaining clusters. The ground pixel distance is the vertical distance, so the distance in the y direction, between the bottom center pixel and a cluster centroid. This metric was chosen to introduce a bias toward balls that are closer to the robot. So if 2 clusters are very similar in density, the one closest to the ground pixel will be chosen. In summary, given multiple valid candidates, I find the 2 clusters with the top densities. If the first place density is significantly greater than the runner-up, then that cluster automatically wins. Otherwise, the cluster with the smallest ground pixel distance wins. In the event of 2 identical clusters in terms of density and ground pixel distance, the program will choose the cluster it encounters first. After choosing the winning cluster, the program then calculates the correction angle. From here, I moved on to the ROS implementation. For the sake of time, I'll keep this next section brief. To implement the entire program into ROS, I split the project into 2 ROS packages. The first package is called NumPy messages, which is essentially just a package that allows me to transfer NumPy arrays back and forth between nodes. The second package is the main package where all of the coordination happens. This package consists of 5 nodes, which is the camera tuner, the photographer node, the ball detector node, the data processor, and finally the robot controller. In terms of communication, the program proceeds as follows. Subsystem 1 captures images and sends them to Subsystem 2. Subsystem 2 then runs the ball detection algorithm, and And once the threshold's reached, it sends all of the detections to the data processor. The data processor then runs the k-means clustering, the voting, and then the angle calculation, and sends the angle back to subsystem 2. Finally, subsystem 2 sends the angle to subsystem 4, which is the robot controller, to move the robot. So just to record some live commentary while the program runs. So at the top left is going to be the video feed, the live feed. So that way we can just see how the robot responds when it moves. On the bottom left is the detection. So just showing the user if the robot is detecting well. Then we have the k-means display, which is more of a debugging thing, just to show, hey, these are the clusters that are detected. And then the robot moves through the angle that it calculates. Well, actually, so what I found out about halfway through the project is the angle that I calculate is the wrong angle. What I mean by that is it's a good angle. It's actually the angle if you're rotating the robot about its x-axis, but I want to rotate the robot about the z-axis. So what I do is I scale the calculated angle down by 5, just to get the angle small enough that instead of overshooting, the robot will instead undershoot, and then be able to, over multiple passes, converge on the tennis ball that it detects. So for example, if there's a large angle, say 66 degrees or so, the robot will start at 12 steps. Then it'll move to 9 or 7, and then it'll get down to 4, and eventually it'll get to 1, at which point it will oscillate between -1 degree movements and +1 degree movements, which means the robot has converged on the tennis ball. I'm very happy with how this project turned out, but there are some things that could use improvement. For instance, the angle calculation, having a way to either have the robot converge more quickly or have some association between, say, the angle about the x-axis and the actual required z-axis would be useful. Or maybe if there's a way to calculate the angle directly, maybe through projective geometry or some other method. I think those are all avenues that are worth exploring. So the second thing is real-time parameter adjustment, and this is in regards to the ball detection algorithm. It's still sensitive to lighting, and currently the camera tuner makes the program more flexible because the user can simply run it if they change the environment, and the parameters will be updated to the ROS parameter server so the relevant nodes can get the information. But it would still be useful to have a way of updating the parameters on the fly as light changes in the environment. Finally, similar to Project 1, exploring other ways of detecting tennis balls could be useful. I'm pretty happy with how the detection goes now as far as noise reduction and choosing a cluster and things like that. But if there's a more direct way of identifying tennis balls, it's worth exploring. I had a really great time working on these projects. They were really fun, and I learned a lot in the process. I look forward to using more computer vision in the future.